Hi, everyone, and thanks for joining my session today, which is on Postgres and, well, especially benchmarking Postgres for vector search performance. So we're going to look into how you can use Postgres as a vector database. And if you do that, what kind of performance can you expect? How can you measure it? And what things to consider when you run your own benchmarks in a vector search use case. A few words on myself before we start with the technical deep dive. So I'm Daniel. I'm co-founder of Benchant. We're a company that is basically running database benchmarks for customers. I have a research background that is also centered around performance assessment of distributed systems, distributed database systems. And I love to discuss and enjoy talking about performance measurements and demystifying the black art of database benchmarking. And apart from all the tech stuff, I love to play every kind of racket sport. So let's actually start with the technical stuff. And as starting point, let's have a look at one of the hot topics in the database world these days. Here we can see a Google Trends chart for the term vector database. And well, it's obvious that over the last 2 years, these type of database got tremendous attention. Of course, driven by the AI hype. And well, all the architects that now build AI applications need to decide if they want to go for a established SQL or NoSQL database or use one of the, brand new vector databases. And well, there are plenty of them already out there. And well, it can be expected that the database landscape in that area is further growing. But of course, all the established SQL and NoSQL database vendors also have released their vector search extensions to compete with these vector native databases. Today's talk gonna be about just one, the elephant in the room. With Postgres, which is also, still and became even more popular over the last years as an open source database with a very strong community and ecosystem. It supports a variety of extensions to basically support every kind of database use case. And of course, this also goes for the AI machine learning use case. So if you want to use Postgres for vector search, this is what we're going to talk about today. By first focusing on what are the options if you want to use Postgres for vector search, and then dive into the performance capabilities. But as already said, vector databases are, let's say, the new thing in the database landscape. A few words on vector databases themselves. So vector databases basically support the storage of vectors, which are a list or an array of numerical values. And vector databases provide dedicated data types to do that. Apart from that, in consequence, they support storing embeddings, which are m vectors of n dimensions that represent a compressed and low dimensional type of data from the real world, which might be text, video, audio. Embeddings are typically created outside of the database engine. There are also approaches where the database is able to do that. And vector databases provide similarity search capabilities where they follow the algorithms of the approximate nearest neighbor class. Moreover, the vector database, the vector data needs to be indexed by specialized index types to enable fast search queries. There are multiple index types out there, just to name here a few. So inverted file index or hierarchical navigable small world graphs as two of the well-known one. There are many more out there. And if you want to dive into vector databases in general, you're going to find tons of material out there. I personally can recommend the following blog post series on vector databases. So this was a rough overview on vector databases in general. And when we talk about Postgres and the Postgres ecosystem, it's not surprisingly that there is not only one extension that enables vector search with Postgres. There are multiple ones. I put here 4 on the slides. There are many more out there. Probably one is just now released. So pgvector is the, let's say, the most known one. The others are a bit more recent. In general, we see that they're all comparably in an early stage, but that's, of course, given the nature that vector databases are a brand new thing. And these extensions also differ when it comes to their feature set. If they differ when it comes to their performance, we're going to look in the second part of the talk. Here is a very brief overview on how they differ. So when it comes to index types, well, they support different kinds. When it comes to the quantization approaches they support, there's also difference here. And then, of course, they have unique features such as, well, pgvector is the most well-known one so far. This is also available in some of the database as a service offers, especially the ones of the hyperscalers already. We have pgvector.rs that supports very high dimensions, and it enables to create the index out of the actual Postgres engine. Or a similar approach is followed by Lantern. We have pgvector scale, which is maintained and released by Timescale. Adds another index type and builds directly on pgvector. And it's also available in the cloud, for instance. This is a very rough overview on where they might differ. Of course, if you want a full-fledged feature analysis, there's way more stuff that need to be considered and in-depth analysis to be done. But that is basically to outline that on the feature level, there are differences. And when you want to build your application and use Postgres as the database for vector search, well, you have a lot of choices. And of course, the decision gets even harder with all of these options. And if we now look more on the performance side, there might pop up several questions, such as which index type should be used for my specific target dataset? Which throughput and latency numbers can I expect based on the available hardware that I have to run Postgres? And of course, which Postgres extension provides the best performance for my use cases, if performance is one of the key criteria? In order to answer these questions, well, if you're lucky, you might find already a report. You find a report that already analyzed this, especially for your use case. It's probably not the case. So you have to run the measurements or benchmarks by yourself. And in order to do that, well, good news is that there are already frameworks, benchmarking suites available that allow you to do that, because with the momentum of vector databases, also a lot of benchmarking suites have been published either by academia, by the community, or by vendors that allows you to benchmark vector databases. So here I put down 5 of them. All of them support Postgres. If you want to have more details on them, or also want to follow or want to have a continuously updated list on database benchmarks, including vector benchmarking, feel free to have a look at our blog where we maintain this kind of list. And when we talk about benchmarks, of course, it's all about the metrics. As we are all know well about benchmarking and performance and so on, it's not surprising that throughput and latency and performance cost ratio are important metrics when it comes to vector database benchmarking. But there's also a fourth relevant metric. So it's recall, which measures the search quality. So in particular, what percentage of the returned results are objectively the closest to the query vectors. And yeah, these four metrics are then the, let's say, most relevant metrics if you do vector database benchmarking. And with that brief overview on the tool set and the metrics for benchmarks, we can dive into the Postgres vector search benchmarks. In the rest of the talk, I will provide you an understanding on the knobs and bolts to consider if you run vector benchmarks for Postgres, but also for other vector databases in general. And we will look into, well, what is the performance index of using different index types? What is the performance index on having different dataset characteristics? So number of vectors, dimensions of vectors. And we'll also look into the performance of different Postgres vector search extensions. And therefore, we carried out, before we dive into the results and the methodology, there are many more objectives that I would like to cover, but that's way out of scope for this talk. So we won't look into comparative benchmarks against other vector databases. In addition, running or talking about an in-depth benchmarking for each of the extensions, it's also not possible in that short amount of time, because every extension comes with their own set on parameters where you can further tune for optimal performance. So for today, we only have to live with the default settings. Same goes for Postgres configuration, where Postgres configuration tuning, it's an art for itself. So here we used a slightly tuned setup, but we didn't tune Postgres to the limit for the vector search use case in that talk. So that's just a disclaimer and stuff for some other talks. Our methodology is that we execute the benchmarks with our internal framework that fully automates the benchmark execution, from spinning up cloud resources, deploying the database on top of it, configuring it, spinning up virtual machines to run the benchmark suits, orchestrating everything and collecting the results, metadata, monitoring data in the end. If you're interested in more details on the framework itself, feel free to have a look at the scientific publications that we have in that context. As benchmark suite, we use VectorDB Bench. As I said, it supports Postgres. It has a great momentum these days by community contributions. And well, with Benchend, but also based on my academic background, we always publish all the benchmarking data together with the applied configurations for full transparency and also for reproducibility. If someone wants to use the results or extend them, build upon them, or just want to have a look if we misconfigured something, feel free to blame us. So you can find all the data on GitHub. Few words on the technical details. We use the latest Postgres 16 version. We're looking into pgvector and pgvector.rs. As I said, we use Postgres not with the default configuration, of course. We used a slightly tuned configuration by pgtune. It is a single node instance that runs in the OVH cloud. And we use VectorDB Bench, not with the latest version. We integrated the 009 into our framework and did some extensions to it. So added some other vector databases that is not of scope for today. We also added CLI support and the option when to create the index. Both of these features are now also implemented in the latest release of VectorDB Bench. That's just as a side note. A few words on the workflow of VectorDB Bench. So there is a load phase where the actual data is ingested. It's optional to create the index before ingesting the data. Then there's an optimized state where, well, it's another option to create the index here. On one of the two options, the index needs to be created. You can apply any database specific tuning here as well. And then there's the query phase where the search queries are executed with an increasing number of threads. And VectorDB Bench comes with multiple data sets for the benchmarks that we're going to show in the following. We use these two comparably smaller ones, one with 1 million vectors, the Cohere one, and the OpenAI with 500,000 vectors of different dimensionality. So these were the basics on the methodology and the setup. So let's start with the first results. First, we were looking into which pgvector index type provides the best performance. And here we're looking first at the ingestion performance for the load phase. So that combines index creation and ingestion into the database. And we see the darker blue bar shows the results for the IVF flat index type, while the light blue shows for the HNSW and then for the Cohere and for the OpenAI dataset. It's easy to see that the IVF flat index creation is way faster than the HNSW. So if we look now at the throughput that is achieved with the respective index types, we can see that here the search throughput is much higher for HNSW for both datasets. And also, not surprisingly, the P99 latency is much lower. As already pointed out, there's also the fourth important metric, which is recall. Here, for these two index types, for that dataset, there's not much of a difference between the two index types and their recall, which is between 95% and 98%. So that was the first, benchmark or case study that we're looking into, the impact of the index type. The second one is about index type, but when is the best time to create the index? So create it on an empty table or create it on an already loaded table. And we also looked into that. The blue chart shows the approach where the index is created before actually ingesting the data, while the purple one shows the time for ingesting the data during the load phase. And in the optimized phase, is it just for creating the index? And the total bars, it's obvious to see that the approach where you first ingest the data and create the index on top of that is much more efficient. This is also the recommended way by pgvector, for instance. But it's also important to know that, this is a database specific recommendation. So if you, for instance, run benchmarks against Elasticsearch, there it's vice versa. So there you should create the index before ingesting the data. In the third case study we're looking at, we looked at the extension pgvector.rs, which provides different index types together with the option in VectorDB Bench to apply different quantization options. pgvector also supports that, but not yet via VectorDB Bench and not in the extension of pgvector.rs. And in summary, we can see here the blue chart, which HNSW with no quantization enabled, compared to the green chart with the IVSQ8 index with product quantization enabled. It's 3 times higher search throughput. And yeah, again, latency is lower. The interesting aspect here is that if we use quantization, we have to keep in mind that this will impact our recall. And yeah, if for that case we look at the recall value, results, yeah, we have roughly 10% less recall compared to HNSW. As the last case study that that I want to present today is having a comparison between pgvector and pgvector.rs. But as a disclaimer, we were using the default configs for both of them. So we didn't tune any of these extensions at all or to their limit. So there is definitely space for improving the performance for both of them. So on the left chart, we can see the load phase. So for ingesting the data and creating the index, here we can see that pgvectors is definitely faster than both approaches with either creating the index on an empty database or on a loaded database with pgvector. But on the right chart, we see that performance is significantly higher for pgvector. Again, there also might be there are already now some improvements to the bindings in vector-db bench for both of these extensions that also might enable new configuration options to further tune each of the bindings. Latency-wise, yeah, it's also obvious that pgvector has a way lower P99 latency. Recall-wise, they're more or less doing the same ballpark. So these were now 4 case studies where we looked into different aspects, and yeah, well, we see that there are clear differences between the performance that you will get. You also seen some performance numbers that you can expect for these very specific data sets and these specific hardware. Of course, our recommendation is always to run the measurements by yourself for your very specific use cases. And it also brings me to the conclusion of my talk. Well, the vector database market is comparably new, still evolving. Same goes for the ecosystem of Postgres with their extensions. And the vector search extensions are also still evolving and growing. They differ in their feature set, but also in their performance capabilities. And benchmarking, well, in general, but especially the vector databases and the vector extensions, supports you in selecting the right technology for your performance-sensitive use case. There are many knobs and bolts that you need to consider when running the benchmarks, or of course, when operating your database system that impact performance. I showed you some today. There are many more out there. So carefully define your benchmark setup if you want to compare different systems. And also carefully read through reports that are published if they have considered all the knobs and bolts. They should. So I hope I got you at least a brief overview on vector search benchmarking in the context of Postgres. If there are any questions, I'm always happy to answer them, so feel free to shoot an email. And if you're interested in database performance measurements in general, well, feel free to have a look at our monthly newsletter, Data Scale Fail, where we publish our latest benchmarking studies on the database world. So thanks for joining in.